So what is synchronization? So let's see what is synchronization. Okay. So this is a mechanism. I mean, synchronization is a mechanism that ensures consistency across shared data. All right. So if you come back to this part, okay, I have briefly explained what synchronization mechanism is. So when there is a critical section as in the set of instructions which is modifying the commonly shared variables. Okay. So when there is a critical section, we put some code just before the critical section and we put some code just after the critical section. So these two combinedly creates the synchronization mechanism. All right. And these two part enables us synchronization among multiple processes. Okay. What about data consistency? So if you go back to the previous example, so this P1 was doing count plus plus and P2 was doing count minus minus. Okay. So over here we have not used any synchronization mechanism. As a result, we could see depending on the order of execution, sometime count is having final value as plus 1 and sometime count is having final value of minus 1 also. Okay. So this is data inconsistency. Alright. So this is race condition. So by using the synchronization mechanism, our one of our main target is to avoid this race condition so that we never end up on such inconsistent system. All right. So if I go back to the definition, okay. So yes. So in the previous example, no synchronization was used. As a result, data became inconsistent. Okay. I have already showed you this example. So depending on the order of execution of processes, value may get changed. That I have already explained. Depending on order of execution, sometimes count was becoming how much? Plus 1 and sometimes it was becoming minus 1. Okay. So this is inconsistency which is called race condition as well. We do not want to end up in such inconsistent system, and that is why synchronization comes into the game. All right. So in a single line, synchronization is a mechanism enables us in achieving a consistent state where there is no race condition when there are multiple processes working in a preemptive multitasking environment. All right. So now let's go to the next part. Okay. So this is the next part. So there are two type of synchronization mechanism. First one is cooperative. Okay. This is cooperative and second one is competing. Okay. Let me give you the example first, then we'll understand it better. So cooperative system is, let's say there is a producer, okay, and there is a consumer. So there is a synchronization between producer and consumer. Producer says, oh, there is a common shared space. Producer says, I will produce and will store my produced item into the commonly shared space. And consumer says, okay, once producer is done with producing, okay, and I have at least one item to consume, I will go and will consume from this commonly shared space. Okay. So once producer produces, then consumer consumes. So there is a cooperation between producer and consumer. All right. So this is called cooperative synchronization. So the synchronization mechanism that helps us to achieve this such a thing where producer is producing, consumer is consuming. So the synchronization mechanism which enables us to achieve such scenario is called cooperative synchronization. Okay. So over here, our main purpose is to maintain the correct order of execution. So once producer has produced something, then only consumer will come and will consume something. All right. It should not be the case that producer has not produced anything, but consumer is trying to consume something. All right. This should not be the case. All right. And another one is ensure data consistency. So when there is a commonly shared space, I have already showed you that some inconsistency may come up. We will have to make sure that there is no inconsistency among the data also. All right. So next one is competing synchronization that I have already told you. So what is competing synchronization is, okay, let me give you the example first. Okay. So what competing synchronization is. So if you come back to this example, so count is a commonly shared variable. Okay. And P1 is trying to do this count plus plus and P2 is trying to do this count minus minus. All right. So P1 and P2 both are competing with each other to get access on count variable. Okay. If you see this example, P1 is trying its best to achieve count plus plus and P2 is trying its best to achieve count minus minus. P1 doesn't care P2 is doing count minus minus or not, and similarly P2 doesn't care whether P1 is doing count plus plus or not. Okay. Neither P1 cares nor P2 cares. Both of them are competing for count variable. So the synchronization mechanism which enables us in such a scenario, all right, which enables us to achieve a consistent state and to avoid a race condition, that is called competing synchronization. All right. If I go back here, okay, so I was This is cooperative and I was here competing. All right. So multiple processes accessing the shared variable. And what is our main purpose? Avoid the race condition. Race condition is in different execution order and different final value of the count variable. We do not want to end up in such a scenario. So we'll have to avoid this race condition. And 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 how we will be able to avoid that? We will be avoiding that by ensuring ME. What is ME? ME is, let me write it down. ME is mutual exclusion. Okay. Mutual exclusion says in the critical section part, if process 1 is present, then process 2 will not be coming into the critical section. Okay. So when, that means when P1 is, okay, let me erase it. When P1 is accessing the shared variable, let's not write critical section, let it be shared variable. When P1 is into accessing the shared variable, once P1 is done with accessing, then only P2 will come and P2 will access. It should not be the case. Once P1 is into shared variable, okay, P1 is accessing the shared variable, all of a sudden P1 is preempted, P2 is scheduled, and now P2 started accessing the shared variable. It should not be the case. Okay. So in a single line, what is mutual exclusion? Mutual exclusion is at a time only one process will be accessing the commonly shared space. Okay. In other words, at a time only one process will be into this its critical section. So if you go back to the previous example, I'll keep on going back to this previous basic example. So if you see, this count plus plus is a critical section because this is set of instruction. These two set of instruction are managing a commonly shared variable which is called count. All right, count plus plus is broken into these three instructions. Count minus minus is broken into these three instructions. So as a result, this is also critical section. This is also critical section. So achieving mutual exclusion says when P1 is inside the critical section, once P1 is into the critical section, P2 will not be into the critical section. P2 will execute its critical section only when P1 is totally done with execution of this critical section. Alright, similarly vice versa. When P2 is completely done with the execution of this critical section, then only P1 will get a chance to get into the critical section. It should not be the case that, oh, P1 has executed only one line, then P2 is scheduled, or vice versa. Let's say P2 has scheduled only one line or two line, and then P1 is scheduled. Okay, this count plus plus is scheduled. This is not the case when I say mutual exclusion. All right, I hope this is clear, but going forward mutual exclusion will be much more clear to you, no worries at all. Okay, so now the next thing is when you should think about the synchronization solution. I mean, when you should think that there might be some issues where you will have to think of some synchronization solutions. So the first thing is there has to be critical section. Critical section is when there is shared resources across multiple processes and there are a set of instructions, okay, which is accessing the commonly shared resources. Okay, so that is called critical section. So there has to be critical section. And one more thing, there multiple processes will have to compete with each other. Okay, it is for count plus plus. Okay, let's say P1 is also competing for count variable and P2 is also competing for count variable. This is kind of competition. And the another one is preemption. Okay, when we are in a non-preemptive system, we don't have to think of any synchronization algorithm because, so in previous example, why the problem started? Because P1 was preempted even before completing the critical section. P1 was preempted here, or P2 was preempted at this line without even before completing the critical section. So if preemption is disabled, then P1 will be completed, then only P2 will be get scheduled, and vice versa. So what will happen in that case? We don't have to think of any synchronization algorithm. We are good to go. So when these conditions arises, then we will be saying, let's think of some synchronization algorithm as of now. Okay, so I have explained what is mutual exclusion. ME for mutual exclusion. What is mutual exclusion? Only one of the competing processes can be in its critical section at any time. Okay, let's say this is process P1, this is process P2. There is some non-critical section block, code block, then this is critical section, then again non-critical section, then again critical section. Let's say in critical section this shared resource is getting used. Okay, in P2 also there is non-critical section, there is critical section, there is critical section. Using all these critical sections, let's say there is a commonly shared resource and this is getting used. Okay, now mutual exclusion says once process P1 is accessing the shared resource either from this critical section or from this critical section, P2 will get a chance of accessing the shared resource only when P1 is done. Okay, so when P1 is into this critical section, all right, P2 will get a chance into entering this critical section or accessing the shared variable only when P1 exits this critical section. Okay, it should not be the case that P1 is preempted in between and P2 is getting scheduled. It should not be the case. Once P1's critical section is finished, then only P2 will get a chance of execution of this critical section. Similarly, when P1's this critical section is getting started, okay, then none of the critical sections in neither this one nor this one will get a chance to access the shared resource. Once P1 is entered, P2 will have to wait till P1 is finished. So when P1 exits this critical section, then only P2 will get a chance to execute either this critical section or this critical section. And why so? Because using these critical sections, P1 and P2 are using this commonly shared resource or commonly shared variable. Alright, if P1 is accessing critical section, then P2 should not be executing critical section and vice versa. Alright, I have explained this thing. Fine. So let's say this is critical section and this critical section is accessing the shared resources. Over that example, this shared resource was count variable. And just before critical section, there is an entry section, and just after critical section, there is an exit section. Okay. So this entry and exit part is responsible for making sure that only one process is accessing the critical section, as I have already explained. If P1 is inside critical section, then P2 cannot get into the critical section. So once P2, I have explained here, once P1 is into the critical section, P2 cannot execute these critical sections. Okay, P2 can execute these critical sections only when P1 is coming out of this critical section. Okay, fine. So if P1 is inside critical section, then P2 cannot get into its critical section where the same shared memory is used. Okay. So let's say this is the same shared resource that is getting used by this critical section and this critical section. Okay, let me make it more complex. Let's say okay, let me erase it. Let's say there is another one shared resource. Okay, and this critical section is accessing this and this critical section is accessing this. So once process P1 is getting into this critical section, then P2 cannot get into this critical section because using this critical section also, the same shared resource is getting used. So what I have told, once P1 is into this critical section, P2 cannot run this critical section. Once P1 is done, then only P2 can execute this critical section. But once P1 is into this critical section, P2, I mean P2 can happily run this critical section. And why so? Because this critical section is using this shared resource and this critical section is using this shared resource. So once P1 is into this critical section, even though P2 cannot run this critical section, P2 will have to wait till the finishing of this critical section from the P1's end. Then only P2 can execute this critical section. But simultaneously, P2 can run this critical section. Okay, because this critical section is accessing some other shared resource and this critical section is accessing some other shared resource. So what I have explained over there it was written that, okay, let me go back. Yes, if P1 is inside critical section, then P2 cannot get into its critical section where same shared memory is getting used. Alright, I have explained this thing. Okay, so far I have given you two type of synchronization mechanism. One is cooperative and another one is competing. Now let me explain two more type of synchronizations. One is busy waiting, another one is without busy waiting. So what busy waiting synchronization is? So there is a famous example with the dressing room example. Okay, let's say there is a shopping mall and there is a dressing room. Okay, so I'll keep on referring this same example again and again so that you can relate it much more better way. Okay, but unfortunately, let's say there is a dressing room, but unfortunately there is no door which you can lock. Okay, there is only a curtain kind of thing. Okay, there is a curtain kind of thing, and also there is a tag. Okay, tag. This is not a lock. This is just a tag. This tag says whether someone is inside the dressing room or not. If someone is inside the dressing room, the other person will have to wait till the guy comes out. Okay, there is no gate, there is no lock, there is just a curtain and there is just a tag. If someone is inside the dressing room, other person will have to wait for that person to come out, then only other person can get into the critical section, not critical section, into the get into the dressing room. All right, so this busy waiting synchronization algorithm says when a process cannot get into the critical section, okay, that process keeps on checking whether he has a permission to get into the critical section or not. Okay, so if I try to relate this thing with this dressing room example, there is a person one or process one. Okay, over here person means process, in terms of operating system. Let's say there is a person one and person two comes and person two sees tag is set, okay, not available. Okay, so now what person two does is person two keeps on checking the tag, not available, not available, not available, and he keeps on checking. Okay, every second he keeps on checking. Okay, so what will happen in that case? Person two will waste his time. Okay, In operating system concept, your CPU will end up wasting time. CPU's time is very much precious time. We should not be spending or should not be wasting CPU time. Okay, so this is a busy waiting solution. Let's say there is a critical section, there is a shared resource, and P1 is executing. Okay, P1 is into the critical section. P2 keeps on checking that whether P1 is done with the critical section or not. Hey P1, are you done with the critical section? Hey P1, are you done with the critical section? P2 keeps on asking this question. So it leads to CPU wastage. Okay, this is a busy waiting solution. And there is one more algorithm, one more kind of solution that is without busy waiting. So what is without busy waiting? So let me help you explaining from this example. So let's say P1 is into the critical section. Now P2 has come. So in without busy waiting, P2 will not keep on asking, hey P1, are you done? Hey P1, are you done? Instead of that, P2 will go and P2 will sleep, expecting that once P1 is done with the critical section, P1 will come and P1 will say, hey P2, please wake up and go to the critical section if you are trying to. I mean, if you want to. Alright, so this is without busy waiting. In this example, no CPU cycle is wasted. Okay, so this is two type of synchronization algorithms. So here I have explained what is busy waiting. So there is a entry section, then there is a critical section, there is a exit section. Okay, I have already explained. So in ways and in so in busy waiting, once a process cannot get into the critical section, what happens is that process keeps on making a loop into here. Okay, so that process keeps on making a loop and CPU time is getting wasted. So P1 stays in a loop. Okay. So can I enter into critical section? This is a question that P1 keeps on asking. As long as P2 is inside the critical section, P1 keep on asking in a loop. That what is something that P1 asked? P1 asked, hey P2, are you still in critical section? Hey P2, are you still in critical section? Once P2 says no, I am not in critical section, then only P1 has the permission or P1 gets the permission to get into the critical section. So here what is without busy waiting? So the process that cannot get into the critical section goes and sleeps. You will see the sleep part in much more deeper way. No worries. Okay. So as of now, just get to know the process goes and sleeps. All right. So once this critical section is freed, I mean when I say critical section is freed, I mean the shared resource is freed. Okay. The sleeping process gets signal and again tries to enter critical section. And who generates the signal? The process which earlier occupied the critical section part. Okay, so in dressing room scenario, I have already explained. Let's say this is a dressing room, there is a curtain and there is a tag. So once P1 is inside this, P2 comes and P2 says, oh, this dressing room is occupied. Instead of waiting and every second checking whether P1 is done with using the dressing room or not, P2 goes and P2 sleeps somewhere. Okay, when P1 is done with accessing the dressing room, P1 goes to P2 and says, hey P2, now please wake up. I am done with using the dressing room. Please go. If you want, please go ahead and you can use the dressing room now. Okay, so this is the dressing room example. So in synchronization part, this dressing room example is a very, very well known example. Okay, so this, and why so? Because using dressing room example, I will be able to explain you much more better way and you will be able to understand in a much more better way.